Hello and welcome to NARC Live on Wednesday the 19th of August 2026. And he said 4 then, for some strange reason. Coming to you live from Norfolk on the east coast of England with Tammy M0TC.
Hello.
And me, David G7URP. Lovely to see you again. On tonight's show, Mike Richards G4WNC joins us for software-defined radio, he promises, without the maths. We bring you some pictures from our GB0HL special event for Lighthouses on the Air weekend from Haysborough Lighthouse last weekend. And we find out what on earth this is. We've had some entries. Can't say whether you're right or wrong, but if you would like to enter now, then please do so either on BATC or on Facebook, and we'll try and include your answers when we can. So, firstly, before we look at the Lighthouse last weekend, we're looking forward to this weekend. We've still got some summer events happening. And this Sunday, it's the last Fox Hunt direction finding competition of the year by last year's winning team, Tornado. Now, it's a bit different because it's on Sunday, and it's a fun hunt. Usually has a twist or two in it. And it starts at 10 a.m. on Sunday and finishes by 1 p.m. or sooner if everybody finds the fox, which of course they will. But there's one little difference is we love using Thorpe Recreation Ground for our normal hunts on Monday evenings. However, on Sundays, like most recreation grounds we've found, it's full of footballers, not unreasonably, playing football and everything, and we kind of get in the way of them, and they probably get in the way of us a little bit. So we've been trying to find somewhere else to start it from, and we have. So thanks to several people from the Fox Hunt team, from Team Tornado, help, we're going to start from Rackheath Village Hall. It's actually quite close to a football ground, but it's got its own little piece of ground. It's got its own car park, and it should be free on Sunday morning. One of our members went and had a look at it last Sunday morning, and it looks absolutely ideal to start from. So the hunt starts at 10 a.m, which really means you need to arrive earlier than that, probably around 9:30. That's the time I'll be getting there as well. Usual rules apply, minimum of 2 people per team. You can use any kind of technology direction finding. It's map 134, which it usually is, and it's that one as well on Sunday. All we do ask is, because it's a Sunday and because we'll finish about lunchtime, we're going to sort some food out nearby. So please register with us if you are going to put in a team. Just tell us how many people, and also if you've got any specific dietary requirements. Drop me an email to that usual address, radio@dcpmicro.com. If you could do that by Friday evening, please, so that I can confirm numbers with the place we're going to eat. So that's this Sunday, 23rd of August. I know it's probably going to be mainly regulars, but if you've been putting off having a go at fox hunting, this would be quite fun and an easy way of doing it. So there is the main details. If you want more details, just drop me an email and I'll send you more than that to you. So as I mentioned, last weekend was the International Lighthouse and Lightship Weekend. It is an international event. Hundreds and hundreds of radio amateurs and clubs put on stations throughout the world. Do you know the biggest country, the most popular country that puts in the most by a long way of special event stations? Germany. We noticed we got an awful lot of German contacts, partly because of the conditions, I guess, made us a lot of our signals were getting into that part of Europe. But we wondered why there were quite so many, and then we looked at the list of all of the registered light ships and light houses, and there were a lot of light ships as well from Germany. So it's obviously a very popular event there. Anyway, I won't say any more right now. Tammy's made up a nice little video montage of some of the pictures that we took and that you sent to us. So have a look at this. Maybe you shouldn't wear shorts at the top of a lighthouse. I've just discovered someone else took that picture, but obviously. Anyway, thank you very much for all those pictures that you sent to us. And thanks especially to all of you who helped us put that event on. There were over a dozen members who actually activated and operated, and several more came to see us, especially on the Saturday, which was fantastic. And just for you interested in what we did run VHF and UHF on the Saturday only. That's because we could only access that top part of the lighthouse on the Saturday because it was open to the public on the Sunday. For that, we used the Club's 9700 and we used a long X510 collinear, which is really long, collinear antenna up there. We didn't use any linears or anything like that, so we ran up to 100 watts, but we made loads and loads of contacts on that as well. On the Saturday, we also ran HF on voice downstairs, right in the basement there, where you saw some people working. Again on the Saturday, because there weren't lots and lots of people there, so the acoustics didn't have such a bad impact on us working voice, which we thought would be the most accessible mode for just about everybody. They weren't great propagation conditions, but still, especially on the Sunday. But luckily on the Sunday we decided to go for CW Morse, because that's an easier mode when there's lots and lots of people talking inside the lighthouse, and people brought their own headsets and things like that to cut a lot of that noise out. So that's what we did on the Sunday, and we made well over 200 contacts as well over those 2 days. So once again, thanks to everybody on behalf of Kevin M0UJD, the organizer, and myself who was there. We were both there all weekend. Thank you very much if you came to help set up, you operated, or you helped us pack up, or just worked us on the air, or came to see us as well. Really good event. Thank you very much. Any feedback for that? Be lovely and well received. It's about 20 years, I reckon, that we've been doing that event from that actual lighthouse. So it's a really, really lovely place to be. Very special because it's the only privately run, owned lighthouse in this country which works. Is a working lighthouse, and it's privately owned by the village. Now, my third bit of news for you, and I have mentioned this before, is the coach trip to National Hamfest on Friday the 25th of September. I have told you about this before. I think we've got a slide which Tammy's just going to put up now. These are the details. We have said these, nothing has changed. It's £30. That includes your entrance ticket. If you leave it till the day, and the early bird tickets have gone now, but if you leave it till the day, you will pay £10 just to get in there, which is still, I believe, really good value for such a big event. But, you know, that does make our trip, which includes that entrance ticket, I think even better value at £30. That's all in. There are pickup points on the east and the west of the city from either Smith's coaches in Blowfield or from the Village Inn on the west of the city as well. You can park your car there free all day, and we will pick you up. All the details are on the booking forms that have gone out with countless newsletters now, and also if you want a printed version, instead of downloading one and emailing it back and paying by backs, if you want to do it the old-fashioned, good old-fashioned way of getting a printed form, filling it in and putting in cash, you can do that by coming to a club meeting like next Wednesday and giving me the form then. I don't know about you, but the months are whizzing by, and Friday the 25th of September is, looking at my watch now, it's probably only about 5 weeks away, something like that. So please do let me have your bookings. They're all looking strong. It will definitely go ahead. I did speak to somebody at the Lighthouse at the weekend saying, well, I'm just going to wait and see if it goes ahead. Well, two things. Firstly, if it didn't go ahead and you'd paid, we would definitely refund you every time. But it definitely will go ahead. So please don't hold back anymore. It really helps me to know numbers, because we've booked a certain size coach. And if we get more than a certain number of people, I need to reserve the next size up coach. That's why. So please, if you know you're going to go, help me a little bit here by booking as early as you can. Thanks very much. Now we've got a bit of members news for you now. Lorna 2E0POI, nice to hear from Lorna. She says, I think she's telling me that she wants to take her amateur radio exam. I know you love that one, Tammy. Yeah. Look at that. Yeah. Our cats will be chewing the end aerial, I think, off of that handheld. But anyway, well, I'm sure she could go in for that, Lorna. Thanks very much for a lovely picture. And one other bit of news, there is a lovely radio station set up at Trimmingham. I'm sure you know about that. It's mainly used, I guess, for contests, but it's used by clubs as well, and individuals, and CBers as well. And it's a wonderful thing set up by Frank and his wife up there. And they've got an open date this Sunday, the 23rd of August. Here's a poster. Doesn't work quite so well on the telly because of the format of it, but there's all the details. I've also been putting that in the newsletters. It's Sunday, the 23rd of August. 12 midday till 4 p.m. And that should be a really good day. If you've been putting off going to see it, this would be a great opportunity to go there, because you'll be welcomed. It won't be just a private event by a club or something like that running it. That's it for me, Tammy. Little People.
Yep, here's the Little People this time. It's Tug of War.
I haven't seen it. Oh, aha, yes.
Do you think they're going to succeed though?
I don't know. It looks like an Apple Power adapter there, doesn't it?
Yeah.
The US one. So trust me to say that. I know that's what you're thinking.
Yeah, pretty much.
Lovely job. This is miniature-calendar.com. Lovely website. Puts up a new picture every day, and Tammy picks one out for us. Thank you.
Our Great Yarmouth correspondent is saying it's very stormy and dark, now having showers.
Oh, yes. And
John,
also, I got an
TWQ.
email. Thank you very much, John. And also, I got an email, just caught it on my phone before I came in the studio tonight to run through everything with you. It was from Martin, G7UGB. Sorry, my mind went blank then. Just to say they've got a full thunderstorm there, and they often lose the internet when that happens. So hopefully you can see us here, Martin. And that's so. But anyway, there is some of that rainy stuff, heavy-ish rainy stuff coming. So take care out there. Now, that competition, when I asked you 2 weeks ago, what on earth is this? Or what on earth is it for? And we've got a few guesses that have come in on them, so we'll read them first. From Mike G4WNC, he says, this week's item is a Shaw durometer used for testing hardness of materials such as rubber. Steve G0KYA says, mystery object looks like a dial gauge. This measures movement on the bottom with very high accuracy. Tony G0MQG says he agrees with Steve. And Bruce G4KZT says, I concur with Steve and Tony. A dial test indicator. Haven't we had one of these before? He says, I don't know, Bruce. We've been doing this for so long now. Probably, I don't know. We started with Who Works in a Shack Like This, and then we went to this about 3 years ago.
I can tell you this is number 140 today.
It's really?
Yeah.
Okay, this is competition picture 140. So it is possible, but I don't think we've had this exact one, whatever. And we haven't admitted what it is yet. Anyway, let's go to the people who emailed us. Steve G3EVA says, this week's item looks like a hardness tester, possibly for soft materials such as fruit.
Leslie G0CIB, it's a Shaw durometer.
Roger EI8KN, nice to hear from you, Roger. It says it's an analog depth gauge, used to be used in the motor industry for measuring the position of a piston when at top dead centre, and many other purposes. So it's a depth gauge or a hardness gauge. They're the guesses so far.
John G8VPE, this week's mystery object looks like a bit like a DTI, a dial test indicator for measuring small linear displacement in an engineering workshop. But as the tip isn't shown in the detail, it might be a low force gauge for measuring a few grams of force.
He's covering both his options there, isn't he?
Yeah.
Okay, Tony M0TDK says, I think this week's mystery object might be some sort of dial test indicator or edge finder. The picture's very small, but my guess would be that it is a whole centre finder. And Tony, he's entered it by email and also on the screen there on BATC, says that it looks like a dial test indicator to him. What is it, Tammy? We can't wait.
It is. Well, I put on the hardness tester, but it is, yeah, what everybody says, a dial test indicator.
It is. It's not a depth indicator, though, really. It's a hardness tester. So you put pressure on the top, I guess, and it tells how hard something is. So that was sent in from Mark G1ALE, your new call sign, Mark. Lovely to see you. He's one of the 8 people who took our full licence course earlier in the year and got his brand new call sign there. So thanks very much for sending us that. Before we meet tonight's guest, then, we've got time for this week's competition, when I'm going to ask you, what on earth is this?
That's a thingamajig.
I know I had one of them years ago in the back drawer. What is that? What is it for? Do you know what it's called? You've got just under 2 weeks to let us know answers to radio at dcpmicro.com. We'll put them on that on the website. We'll also put it on Facebook as well. Don't put your real answers on Facebook though, because it spoils it for other people trying to enter. Just drop me an email to radio at dcpmicro.com by 3 o'clock on Wednesday week, and we will reveal what that is, or what it's for, or what it's called. So we are nearly ready to meet Mike again tonight, but before that, just a quick look what's coming up this week at the club. So on Sunday, as I mentioned earlier, we've got that Sunday Fun Fox Hunt from 10 a.m. from Rackheath Village Hall, but please register with me if you're going to take part. Sunday, 7 p.m, the GB2RS News on GB3MB. On Monday, at 7:30, the Monday Night Net, also on GB3MB. And then on Wednesday, we meet at CNS School. It's a social informal between 7 and 9:30. By the way, the one we met last Wednesday with the eclipse, that was a whole week ago. Where does the time go? It was really, really good. And as you hopefully saw in the newsletter, we had lots of people turning up, and we just had an impromptu sort of eclipse party, really. It's really, really good. And of course, we always want to hear from you. Please do keep sending your details, your pictures, your stories, mystery objects, and of course this card. We're always happy to send to anybody you feel will be shared by a card from your club. Just drop their details. I can hear the rain outside.
Can you?
Yeah, I really can.
On.
And please send us their name and address, and we will be happy to send them a card like this. Now, our next guest is no stranger to this. In fact, I can remember in those very, very early days of the pandemic when we first started doing this, meeting Mike G4WNC, and he came and gave us talks then. And over the years, I'm glad to say he's come back with different talks. And tonight, his talk is intriguing because if you were one of those 8 on the full license course this year, you will know that you do cover software-defined radio, and there's a lot of maths potentially. So Mike's promise to introduce us to SDR without the maths is intriguing, and it's lovely to welcome you back. Mike, welcome.
Hello. Yes, thank you very much for inviting me. It's always good to get back here.
Yeah, and it's lovely to see you, honestly. Thank you so much for all your all those wonderful talks over the years.
That's no problem. I enjoy them.
But this does sound, as I said, this really does sound quite something, because I saw how deep it goes now, the full license into software-defined radio. So we're intrigued to watch your talk tonight. We're going to leave you to get on with it, of course, as we always do. But if you have a question or a comment for Mike or about SDRs or anything else that he's telling us about tonight, then please don't forget to put them onto Facebook or BATC, and we'll read them to Mike at the end. But now, over to you, Mike.
Yeah, yes, please. I love the questions. It's always good. Helps me refine the presentations. If you ask me questions and point out things I've got wrong or a bit weak, then I can make the presentation better the next time. So I originally came up with the idea of doing this a few years ago now, and I have presented it a few times. And exactly because of what David has just said, is that every presentation I've seen that describes SDR seems to very rapidly descend into maths, and often quite advanced maths. I can understand why, because a lot of the principles of SDR are so nicely explained with some complex maths. So if you can remember your complex maths or your higher level maths from school, or maybe you've done it more recently, then those explanations do click into place and make perfect sense. But I know for a lot of people, they've either forgotten all that, gratefully, or never did that stuff in the first place. And so as soon as a presentation disappears into maths, they sort of lose the plot, really. So I thought, well, it ought to be possible. With most subjects, no matter how complex they are, if someone understands it, they can usually explain it simply, and that's what I've tried to do here. So instead of maths, I've got quite a lot of animations and visualizations that explain how things work. Now, in order to do this and make them effective, I have made a few compromises. So the purists there might say that some of these things are not absolutely technically correct, but the principle that I'm demonstrating is correct. And I mean, if you don't think I've made the right compromises, then do tell me. But I've presented it to several audiences, some of them very knowledgeable, and it's all gone down very well. So this is what we're going to cover. Briefly, what is SDR? I suspect most of you know by now. we'll look at some basic principles and SDR types, and we'll look at next generation SDRs. Most of the presentation is on the basic principles of SDRs. So you can understand some of the things we talk about freely when we talk about SDRs that maybe you haven't got to grips with yet, of what all those things really mean or why things work in a particular way. So what do we mean by SDR? Well, it's a very broad description really. It's where some part of the radio signal is being handled by software. Now that can range from just a digital final IF, which is where it first started appearing, that's probably where it first occurred, through to full digital processing right from the antenna. So if you look at, I don't know, a modern transceiver like one of the Flex series, for example, you will find that they digitize the signal just about as close to the antenna as you possibly can, and then everything else is done in software. The great power of that is you can completely change the way the receiver operates by changing the software or the firmware. And as you can imagine, in a military scenario, that's got huge potential when you want different radio sets to work together with each other. You can just plug in some more software and you completely transform your radio set. So there's a few key principles of SDR that we need to understand. The first one is in phase and quadrature. That's the I and Q signals that you see throughout SDR radios. The other is the analog to digital conversion process, how we convert those signals into the digital world. Then there's decimation or downsampling, how we reduce the data rates and make it all more manageable. And then there's those spectrum displays and things where we use fast Fourier transforms, and what on earth are they and how do they work? So we're going to be covering all of those tonight. So your first probably amateur radio introduction to software-defined radio may have been with the SoftRock kits that came out. I can't remember when they came out, it's quite a long time ago now, but they were relatively cheap. They were direct conversion receivers and transceivers. So they mixed down to audio, and at the heart of them, they look something like this. A fairly typical direct conversion receiver in that the antenna connects basically directly to the mixer, and the mixer is at the same frequency as the signal you want to receive, and so the output is audio that goes off to a sound card. The difference, of course, with SoftRock was that there was a second mixer. So it's two identical mixers, and the oscillator, the local oscillator, had two outputs. One was at 0 degrees, called in phase, and one was at quadrature, because it's quarter of a cycle out of phase, so 90 degrees. And so you got two signals come out that were virtually identical, but one was offset by 90 degrees. So that's called a quadrature sampling detector. And they were very popular. There was lots of different versions of those. People spent a lot of time refining quadrature sampling detectors to get the best performance. But then you have to say, well, why use I and Q? It's exactly the same signal. All that's happened is it's been switched through 90 degrees. What's the point? What does that give you? Okay, so we need to look a little bit deeper. So most of our familiar measurements that we use around the shack, our voltmeters, our oscilloscopes, and our SWR meters, are all two-dimensional. We never get a three-dimensional look at our radio signal. And our radio signals are three-dimensional. And so we're not measuring the third dimension here, we're only measuring the two dimensions. So how do we get to see the third dimension? So if I illustrate it here, on the left is a sine wave, and all a sine wave is a spiral or a helix like that, viewed from its side. So if I just play that again, you can see when you look at it from the side, you get a typical sine wave. But if you rotate it to get a three-dimensional view, you find it's a rotating wave, which is precisely what you probably already knew, that a sine wave, if you thought about it, should always be a rotating wave. But we get so used to seeing it with the sideways oscilloscope view that we don't actually appreciate that it's a 3D wave. And in order to do more sophisticated work on this radio signal, we need to be able to see and measure that 3D view. And that's where the in-phase and quadrature signals come in. They give you a 3D view. You can think of it as similar to the way our eyes and our ears work. Both eyes see exactly the same scene, but they see from a slightly different perspective because they're spaced apart. The same with our ears. And what does that enable us to do? It gives us depth. So the reason we can use our ears to tell where a sound is because they're spaced apart. If you cover one ear, you'll find it very difficult to work out where sounds are coming from. The same as if you cover one eye, you'll find it very difficult to get depth perception properly. So you can imagine the spacing of the in-phase and the quadrature signal as being similar to that spacing that we use with our eyes. It sits at the heart of all software-defined radios, but it's used in lots of other electronic applications. And a classic example is, you will know all your modern transceivers have got turn round and round knobs on them. They're everywhere, and the reason they're everywhere is they're just so useful. They're so much better than the old potentiometers that you used to have to get the switch cleaner on and all that stuff. So you can use them for everything from volume control to tune-in to adjusting filters, switching things. So they've just taken over virtually every rotary control on your rig will be a shaft encoder or rotary encoder. And that uses effectively I and Q signals. If you look at the connections to a rotary encoder, there's a ground and then there's two pins. Call them A and a B, for example. So if you turn the rotary encoder in one direction, you get a pulse on A followed by a pulse on B. If you turn the rotary encoder in the opposite direction, you get a pulse on B first, followed by a pulse on A. And that simple technique of having them offset like that gives it this 3D view. It can tell which way you're turning that. So the number of clicks tells you how fast you're turning the dial. Whether A or B precedes each other tells you which direction it's being turned. And that's all you need to use that shaft encoder for any control at all. So it's the same basic principle. So I found the best way to look at how I and Q signals help us with demodulating signals and modulating signals is to look at modulation first, because it's much easier to demonstrate. And if you want to see this for real rather than believe me or anyone else, you can actually build a little test circuit. So here's an illustration. So I built a little test circuit. This is it. It's very simple. For my test circuit, I used a couple of mini circuits double balance mixers for the mixers. I used the good old SI 5351 clock oscillator to provide the in-phase and 90-degree clock oscillator. And then I used a combiner to sum the output of the two oscillators. So that's all I did. And the control ports, the I and control signals are connected to the IF port of those mixers, and that will accept a DC signal. So let's have a look at what that actually does. So on the top here, that's the I signal, and that's the Q signal coming out of the two oscillators. As you can see, they're 90 degrees apart, because out of the two mixers, I beg your pardon, because of the two oscillators are 90 degrees apart, the output of the mixers is 90 degrees apart. So what do you think the sum will look like? Well, it looks like that. It's another sine wave, same frequency, but it's halfway between these two, so it's offset by 45 degrees. Okay, so that's what our output looks like. So let's move on and see what happens if we start changing the value of the I and Q control signals. So what if we reduce the amplitude of the I and Q signals together, so they both come down together? So have a look at this. So not surprisingly, they both go down to 0 and the output follows them. You'd expect that. Now that seems unimpressive initially, you might say. So what's the point of that? But what that means is that we can create amplitude modulation of an RF signal simply by controlling the signal on the I and Q control points. And that's a low-level signal. So we could supply the same audio signal to both the I and Q inputs, and we'll have a modulated RF wave coming out of the combined mixers. So that's a brilliantly easy way to do amplitude modulation. So that's that part. So what if we start changing the I and Q values independently? So here we go. So this time what I'm going to do is reduce Q to 0. So just the Q control signal. So here we go. Watch what happens to the trace at the bottom. So it moves to the left, which you would expect when you think about it, because in that state, the bottom trace is the sum of the two above, so it's going to be halfway between. If you take one of the signals above away, then it's going to move over to the left. Notice it doesn't step over, it moves gradually. So you've got fine control of how it moves to the left. So what then happens if we reduce I to 0? It moves to the right, which again makes sense from what's there. But what we've just proved is we can provide 90 degrees of modulation just by altering the I and Q signals. So we can do phase modulation. So changing the value of I and Q independently alters the phase of the output signal. So that's really useful. But I only did positive values. So I only altered I over a positive value from 0 to 1 and Q over a positive value from 0 to 1. We can actually use negative values as well as positive values for I and Q. And if we do that, instead of the moving the wave over just that 90-degree quadrant of a circle, we can actually access the full 360 degrees of the circle. So you can see that's really powerful. So now with I and Q, we can do amplitude modulation, we can do phase modulation, and frequency modulation is just a form of phase modulation, so we can do that as well. So that covers about every modulation system that's in current use. And I can show you how this works with this next little demonstration. So this polar plot over here on the right hand side, you can imagine that's 0 to 360 degrees. The green blob is where the output is, okay? And Q is on the vertical axis with positive at the top, negative at the bottom. I is on the horizontal axis, positive on the right, negative on the left. So if we move it just a bit, so with a bit of positive I and Q, you can see we get a result in between, which is where we were with our demo. We're 45 degrees of phase shift to there. If we go all Q and no I, we're 90 degrees of phase shift. If we put negative I in, we go round again, another 90 degrees, but we can go anywhere in between that. We don't have to go in 90 degree steps or 45 degree steps. Again, round to negative I only. And so we can go all round the circle like that. So you can see by altering the value of I and Q, we can put that output point at any phase angle and any amplitude in that circle, which is why we can produce any form of modulation using those combined. The great thing about demodulation is that whole principle works in reverse. Okay, so once you can see how that works there for modulation, it works exactly the same way for demodulation. So if we put our signal in, comes in from the antenna, goes into our two identical mixers with the local oscillator 90 degrees out, the I and Q output will effectively be the I and Q versions of whatever modulation is on that signal. So it's just, you can see why it's taken over and made IQ signals so important to software-defined radio. So let's just summarize I and Q signals. So they're a simple way to generate and demodulate any modulation system. And you can achieve the quadrature modulation and demodulation. You can do it completely with analog circuitry, as it was with the soft rock, as we did with our little demonstration here. Or you can do exactly the same thing entirely in software. That makes it really powerful. It's used in pretty much all SDRs at some point, and it's absolutely fundamental to SDR technology. And as you can see, you can hopefully now you can understand why it's such a powerful tool. So that's IQ signals. That was easy, wasn't it? So let's now move on to analog to digital conversion. So I think we all probably know that computers work on ones and O's, and they can only handle binary numbers. So if we've got a radio signal that we want to get into a computer, somehow we have to convert it into binary numbers. And the way we do that is a fairly simple technique, to be honest. We make lots of voltage measurements at regular intervals to try and sample the incoming signal and make a representation of it. And the simple rule, which is Nyquist-Shannon theorem, is that you must sample or measure at twice the rate of the highest frequency or the widest bandwidth that you want to capture. Okay, so if you want to sample the entire 30 megahertz band, then you must be taking measurements at 30 million samples per second or greater. So I've put together an illustration to show how the process works that will maybe make it more obvious. So there, we're just talking about a simple sine wave signal at the moment. So we've got voltage scale on the left-hand side, and we've got time along the bottom showing our sine wave. So a sine wave, this can be any value at any instant. So at each sampling point, the dotted lines represent our sampling points, and notice it has to be regular. And every time our sample point crosses the sine wave, we put a mark on the sine wave. So that's the point we're going to sample. So the way it works is if you were to make a smooth line between those dots, you would come up with a reasonable representation of that sine wave, okay? Just with those dots, just with those measurements. Now, one of the things you'll have here mentioned is the sample rate. The sample rate is the number of times per second that we sample the sine wave. So it's the frequency of these little sample points. So we need a scale to put a number against these sample points. So for this example, I've just used a very crude 3-bit scale, which means there's only 8 possible levels available, which is what we've got there. If we were doing a real radio set, we'd be talking at somewhere between 8 and 16 bits to get enough resolution to get a real reasonable representation. So the next bit is really important because at the moment you'll notice that the dots, red dots, are on the sine wave at the sample points, but they don't actually line up with the numbers on the right hand side. And those are the only numbers we can use. So what we have to do is quantize it, which is that. So if you notice what's happened, all the sample points have moved slightly so that they align with the numbers on the right hand side, because those are the only numbers we can use. So if I go back, so that's the sample points, and in order to quantize them, and that's turn them into a number, we have to choose the nearest number on the scale to quantize it, and so they all move slightly out of line. Now, the problem with that is it creates a certain amount of distortion, because if I was now to trace the path through the resulting points, it wouldn't be quite as good a sine wave as the original sine wave. And the difference between the original waveform and the one that we've ended up sampling is called quantization error or quantization distortion. It's the distortion caused by selecting the next available quantity as opposed to the right amount. So you can see that if we had a much finer scale down here, i.e. we had more bits, we could get much closer to putting all the dots on the right line, on the real line, so we get a more accurate representation. But for now, because we've only got a crude measurement, we end up slipping quite a bit. Okay, so that's what when people talk about quantization distortion or quantization errors, that's what it is. It's in the sampling process, the fact that you have to choose the next available number in order to sample the signal. So we get the numbers repeated down the bottom here, and what we can then do, those are our samples, and that's what we get. We get a string of numbers out the other side. So the basic process, we put an analog voltage in, the analog to digital converter does the sampling and it quantizes that sample and it pumps out a string of digits like so. And ultimately it looks like that. So you get serial digital data on most of the analog to digital converters that we use. That's what we end up with, a high-speed stream of data coming out representing all the sample points as we convert from analog to digital. So here's just a summary of the complete process. How often do we sample? Well, for a wideband transceiver, say a Flex or something like that, or an ANAN, or any of the other modern transceivers that sample the whole of, or cover the whole of the HF band through to 50 megs, would typically be sampling at 122.8 mega samples a bit. That's just a convenient number that works well mathematically. So it then gets into the quantization bit, and the precision would be 8 to 16 bits. For a wideband radio like this one, it would almost certainly be 16 bits. And then the output is a digital stream. The problem is that all that data ends up with one heck of a digital stream coming out. So you would expect to get a stream of about 2 gigabits per second coming out of the analog to digital converter. That's quite a lot to handle. So let's just return to data bits because it's important. So generally speaking, the more bits we've got in our conversion processor, the greater the precision. It means the greater the dynamic range between the residual noise and the signal we can have, and the difference between the weakest and strongest signal is what we're talking about. So if we've got an 8-bit analog to digital converter, we've only got a maximum of 48 dBs between the noise at the bottom and the highest signal it can handle. 12-bit it changes to 72, 14-bit 84, 16-bit 96 dB, which sounds quite nice, but there's actually a catch. So real analog to digital converters offer less dynamic range due to noise and distortion in the conversion process. So typically we use a number called the effective number of bits, and that indicates the practical performance of an analog to digital converter. So if you take the LTC 2208, which is a very popular analog to digital converter, it's used in a lot of high-end receivers. It's a 16-bit analog to digital converter, but its effective number of bits is actually only 12.5 bits because of the noise and quantization distortions, etc. So it's quite a significant drop. But there's a way to improve this later in the process, which I'll show you. So this is just a graphical demonstration of that range of bits. So you can see for the 16-bit, you know that scale that we had on the side of our quantization? Well, on 16 bits, you've got 65,535 divisions. So you've got a much greater chance of finding alignment between your RF signal sample point and a number on the side of the scale. So how do we manage it? So if we've got an 8-bit analog to digital converter, and a typical example would be the SDR dongles. I expect you've all got an SDR dongle in the drawer. They're the cheap little devices, cost about a tenner, that got a lot of people into software-defined radio. They're usually a USB stick. They've only got an 8-bit analog to digital converter. So if you look at that, it's got a very narrow dynamic range. So how on earth do we get such success with them on our radio bands? Well, this is how. What we do between that analog to digital converter and the antenna and the early stages of the receiver, we put a variable gain amplifier. And a variable gain amplifier provides both gain and attenuation. And what we do, we adjust that amplifier to put those 8 bits wherever we want in the sensitivity range. So if you're dealing on a band which is really quiet, you can actually move its sensitivity down to a very low level and it will work perfectly well. Where you hit a problem is contest time, typically, where you want to receive some very weak signals, but you've got someone down the road blasting away. And then you can't handle that dynamic range with an 8-bit receiver and you'll struggle. So the data rates, the way you calculate the data rate, it's simply the bit depth by the sample rate. So if an 8-bit ADC sampling at 10 megabits would be 10 times 80. This is as complicated as the maths gets, by the way. And a high-end SDR 16-bit sampling at 128 megabits is 2 gigabits of data. So it's a lot to process, 2 gigabits of data. So let's look at one other aspect. This is the last aspect of analog to digital converters, and it's aliasing. You will have heard of this, of anti-aliasing filters, etc. If we just look at how the sample works, process works in a slightly different way, you'll see why we need anti-alias filters. So in this example, we've got a signal which is only just being adequately described by the sample points. So you can imagine if I drew a smooth line between these points, I'd probably end up with something close to a sine wave. Okay. But what happens if I put a frequency into this which is much higher and so doesn't have enough sample rates, sampling frequencies? So this one is too high and there's not enough sample points. So you can see that I'm not going to be able to describe anything like this sine wave, because I'm going to go from here down to there, up to there, over to there, down to there. I'm not going to get that sine wave at all, or even anything like the same frequency. So it will record those sample points, but that won't describe that waveform. What it will describe is this waveform, which is a much lower frequency signal. And so what will happen is if you put a high frequency signal that's above twice the sample, or of the sample frequency, half the sample frequency, you will get a low frequency signal fold back into the spectrum. And that's what happens. And that's why we need a filter. So too high a frequency in gives a false low frequency out. And those will pop out throughout the spectrum if you don't have a filter on the front. So the way we overcome that is we have a mixed signal coming in on the left, an anti-alias low-pass filter to cut out all the high stuff, and then we get clean signals going to the ADC, so we get clean digital samples. So it removes frequencies the ADC cannot sample safely. The maximum input frequency is half the sample rate. So if we're sampling at 48 kilohertz, for example, then we'd have a 24 kilohertz low pass filter before it. to tidy up the signal. So that's why we use anti-aliasing filters. So there we go. That sums up analog to digital converters. We use a sampling process to convert the signal. The data rate depends on the bit depth and the sample rate, and we need an alias filter to limit high frequency signals. And we've got very high data rates potentially. So where are we going next? We're going to fast Fourier transforms next. So what about spectrum displays? How do we get a spectrum display out of a string of numbers coming out of an analog to digital converter? That's the question. Now the thing behind this is the Fourier series. So this is a mathematical tool, if you like, formula, where any waveform can be constructed by combining multiple sine waves. So that's what the theory says. Now, anyone who remembers the old Hammond organs that were popular in the 70s, I think, in the pop world, we had one in the band I was in. Those organs have got, and a lot of church organs do the same thing, they've got a whole line of drawbars at the front. And the Hammond organ used to use sine wave tone generators. It was mechanical tone wheels, which were shaped like a sine wave, to generate all the tones. And it would produce all its vast range of sounds by mixing all the different tones together with the drawbars. So you could create all sorts of harmonics to create all manner of sounds. Extremely flexible and powerful, and much the same way as a church organ will create lots of really interesting sounds. That's using the Fourier principle to generate a complex sound by using sine waves. But it also lets us do the opposite, a bit like our IQ work we described earlier. It lets us take a complex waveform, apply the Fourier transform, and disassemble it into its sine wave components, which, if you think about it, is what we want for our spectrum display. We want lots of narrow bars showing you what frequencies make up this spectrum display that we've got. So here's what it does. So we sample a signal here from 0 to 10 megahertz. We apply the fast Fourier transform, and it breaks it down into what are called bins, which is the output, and it tells you how much information is in each bucket, how much energy is in each frequency bucket. And looks a straightforward process there. And that's what it does. Let me just look at it a little bit differently. The FFT size, and you'll see this mentioned on your spectrum displays, you can usually choose the FFT size, and it determines the number of frequency bands or bins, and it's effectively the resolution of your display. So if we had a 10 megs bandwidth and we had an FFT size of 10, we would have each bin would be 1 megahertz wide, which wouldn't be a lot of use. Practical systems use FFT sizes that are usually a power of 2. So 512, 120,024, 4096. That's because it works mathematically better with the Fourier transform if the size is a power of 2. So FFTs are iterative in that you don't just run an FFT and out comes all the data. You have to run it repeatedly. So it means you have to get a sample of the signal and freeze it, and then you cycle over it repeatedly, gradually working out all the energy values in each frequency. So because of that process, if you have a very large FFT, the computer can take quite a long time to iterate through all those measurements before you get your display. That's why on your SDR receiver, if you start increasing the FFT size, you'll notice that the display gets sluggish. It's because it's taking longer and longer to run through all the FFT iterations in order to populate your display. So one other thing you've heard mentioned and you will see on your SDR receiver when you're setting your FFT size, you'll get the option of choosing a window. You might be wondering what a window is in this term. And it's because the FFT operates on a sample of the signal. The ends of the sample have to be joined together to make a continuous loop, so the FFT can iterate over it. If there's a discontinuity at the join, it will cause spectrum smearing. So real signal samples rarely match. So you might pick, say, a 10 millisecond sample of a signal. If you try and bolt the ends together, it's highly unlikely the two ends will match perfectly. So you have a problem. So a window is a filter that normally reduces each end of the sample to 0 so you can join them together without a glitch. So let me just show you that visually and you'll see it. So there's our sample to be analysed. And if you look, if we were to join both ends of that, we've got a glitch. There would be a click. If we join that to that, it will join with a straight line and there will be a click, which will create harmonics across the spectrum display, which gives the smearing that you can get. So if we apply a window shape like this, what it will do, it will reduce the level of the sample at each end, so it goes down to 0. So then we can join the two together and we won't have a discontinuity and we won't have any smearing. Now all the different window types that you see listed, Blackman's and all the rest of it, they're all sorts of different shapes that work better for different types of signal. So some work better for live spectrum displays, others work better if you're just monitoring a sine wave, for example. So that's why they're all there. I won't go into which one's best and all the rest of it, because they're all a compromise, and it's choosing the compromise that works best for you. Generally speaking, the one that's a default on your SDR is probably the one to go with. So here's a look at the sequence of FFT. So we get our sample, we window it, we do the FFT, and then we get our spectrum display. And we get looping. I've also got another little animation here that shows it. As we go through the iterations, you'll see the spectrum display building up there. I'll just run through that again so you can see it. So every time the FFT iterates, it fills another bin and you get your spectrum display up here. So once it's done that FFT display, it then takes another sample and repeats it. And that's why your spectrum display can sometimes seem jittery if you set it up for a very big FFT size. So let's just summarize FFT. So it's used to display a spectrum of the captured digital signal. The size determines the number of bins and the resolution. Large FFT size increase processor loading and slow the display updates. So there we go, that's that. Now we'll just move on. We're getting towards the end of the technical bits at the moment. Hope you're still awake. So decimation and downsampling. So a wide spectrum display is very nice, and I'm sure we've all seen these 0 to 30 meg spectrum displays. And they're sort of a bit of a novelty because they're too wide to use. Really, when we're tuning around on a band, we want a much narrower bandwidth to work with. And when it comes to demodulating the signal, we really only need somewhere around 12 to 24 kilohertz of bandwidth on HF band in order to deal with any modulation system. And so what we need to do is, from our 0 to 30 megs of bandwidth, we need to get a slice out. We need to take a slice of a narrow bandwidth. And of course the other thing is, with our 0 to 60 megs, which is like a Flex or an Anan or many of the popular HF transceivers, they do 0 to 60 megs and the data rate is 2 gigabits a second, which is really difficult to mess with, especially when you've got to do maths on it at that rate. So most people use a device called a field programmable gate array. This is a very complex arrangement of gates, logical gates and logical functions, which is programmable, so you can get it to do a wide range of different things. And you can program these up to do all the heavy work. There's lots of benefits with them. They use parallel processing, so you can get it to do many tasks at the same time. When it's doing decimation, what it does, it discards all the stuff that it doesn't need and filters the result to produce a narrowband receiver slice for us. And it usually creates the FFT spectrum display as well. And the processed data coming out of the FFT gets passed either internally in the receiver, or it gets sent to a PC, or even over the Ethernet or USB. So here's a little visualization of how we downsample. So we've got our 60 megs of spectrum on the left, and we've got our receiver slice, and that receiver slice can be tuned anywhere in that spectrum, and then it's sent off to a narrowband demodulator, which is much easier to handle and doesn't use many computer resources. In fact, some transceivers these days have more than one. I think the Flex 8600 has up to 4 receiver slices that it can generate and have running at the same time. So one of the great things you get out of downsampling is a processing gain. You can imagine this rather like, if you think of our 0 to 60 megs bandwidth that we've sampled, and we've only got 72 dBs of dynamic range, for example. Well, over that bandwidth, if we were to take a smaller part of that, we would get a processing gain, wouldn't we? Because we wouldn't get all the noise of the whole 60 megs bandwidth. We'd only get the noise appropriate for our little bit. So by oversampling and taking only a slice out of the spectrum, we get some huge processing gains. So when we downsample, a bit like adding a filter, we discard loads of noise and artifacts as well as unwanted signals. We take them out of the equation. And so we improve significantly the signal to noise ratio of the wanted sample. So an example, this is a quote from Flex documentation. So the Flex 8600, I know it's a flash radio, but it's a good example to use. They sample at 250 mega samples per second on their ADC. So they go way over the top, double what you would normally use. But their receive slices are just 24 kilo samples per second. That gives them a 40 dB processing gain, which is a lot of processing gain. So if you do the calculation on the 2216, whatever it is, analog to digital converter, which nominally has a 72 dB dynamic range, if you add 40 dBs to that, you end up with 112 dBs of dynamic range. Now that's really looking quite good. And that's equivalent to an 18-bit effective number of bits. So that's really starting to look very attractive to have 112 dBs of dynamic range. And that's what the Flex 8600 has. And that's how it gets it, even though it uses an analog to digital converter, which initially doesn't look that hot because it's only got 70 dBs of dynamic range. But by the time you've downsampled and given it that boost of 40 dBs, you get an amazing dynamic range. So processing gain is important. So the summary of downsampling. The raw ADC data streams are often too fast to handle, so we put them in an FPGA to provide the initial processing and reduce the sample rates, etc. And we get a significant processing gain when we downsample our signals. That finishes the technical bit. Now we go on to just look at 3 receiver options that I just think are quite interesting. Okay, these are my choice. I've picked these as being interesting. You might disagree. So the AirSpy Discovery HF Plus, when it came out, was a completely new and revolutionary design, and it was designed in cooperation with Twente University in Belgium. And for a start, it used N-path tracking RF filters. Now, these are ingenious little switch capacitor tracking RF filters that all you need to do is apply the carrier frequency to the filter, and it will provide a bandpass filtering effect at that frequency. So it makes it very easy to make a tracking RF filter. Normally something that's quite tricky to do in a digital world. And the other thing that it uses, which is quite revolutionary, is a polyphase RF mixer. Now, the use of these two things is significant because the big downside with an N-path tracking filter is it has a very large harmonic output. The great attraction with a polyphase RF mixer is it's a harmonic rejecting mixer. So the two of those go perfectly together. One generates harmonics that are difficult to get rid of. The polyphase mixer gets rid of the harmonics that are difficult to get rid of. And so the two go together to make quite an amazing little receiver. So it's got excellent performance from LF through to 31 megs and 60 to 260 megs. The Discovery version has got some additional pre-selector filters in it. And here's a block diagram, and you can see this looks quite different to a conventional receiver. So on the left-hand side at the top here, you see you've got the antenna and some pre-selector banks. There's an attenuator here, which is all computer controlled. And it's got a power detector, which goes off to the DSP. And it's got another power detector down here. These are all about controlling the various gains through the system to avoid system overload and to optimize the distribution of gains. It's got a low-pass tracking filter there. It's got a bandpass switch capacitor tracking filter there. And it's got a low-noise tracking amplifier there. And these feed into these mixers. Now, this design uses 16 mixers, and the phase splitter, instead of having just a 90-degree phase shift, it's got a 16-phase phase shifter. So 16 phases, 16 mixes, and then it goes through here, and this device is an IQ reconstruction device, which puts all this back together. But it's this combination here, the polyphase mixer with the 16-phase local oscillator effectively, which does the harmonic rejection, which makes the switch capacitor filters up here possible. So once we've got through here to the IQ reconstruction, we're then fairly straightforward. We go into analog to digital converters and then into the digital signal processing cores and away. So you can see it's quite an interesting design, which is why I picked it. And performance, if anyone's got one, you will know it's extremely good performance, very low noise receiver. If you haven't got one, it's well worth a look. So next, I've mentioned them a couple of times before, but I mentioned the Flex 6300 and 8600 SDRs. They are good. They're known to be good. They've been well proven to be good. They direct sample 0 to 54 megs, as close to the antenna as they possibly can. The 6300 samples at 122.8 megasamples per second. The 8600 doubles that to 245 megasamples per second, which gives it a bigger processing gain when you start reducing that down, reduces the noise. All the processing is handled in software. So if I just show you, and they've got multiple receivers within the rig. It uses an FPGA to handle the high data rates. Here's a simplified block diagram of the front end. So at the very front, you've got antenna switching arrangement, so you can choose between different antennas. It then comes into bandpass filters, then into a preamplifier and filter. This is what they call the pre-selector, this little unit here, and that then goes into the analog digital converter. Now in their block diagram, they don't show an alias filter here. I suspect there may well be one, but if not, It may be that these filters here, they just put more work in these filters to make absolutely sure that frequencies higher than half the sample rate don't get in to the ADC. But once you've got to the ADC, it goes to the FPGA, and then it's all digital and being handled in software. So you can see it's really just a sampler. And there's two of these, at least two of these, and I think there's 4 in the 8600. I might be wrong on that, don't quote me on that. But I just wanted to show you the diagram so you could see just what they're like in terms of simplicity, really. There's a lot of design gone into this, but the front end is basically just trying to sample and make it digital as soon as possible. And looking at next generation SDR, one of the things to do is to eliminate the expensive FPGA. FPGAs are a bit of a nuisance because not only are they expensive devices, complex devices, but programming them is not easy. It's a very specialized skill. So it's a bit of an obstacle having an FPGA. But what we can do is utilize the faster and faster speeds we're getting in USBs to send the ADC output direct to the PC, basically. And we can now do that because it simplifies the hardware and the front end just becomes a sampler. And all the SDR processing is done on the PC. There's one device I know that you can get now that does it, which is the RX888 Mark II. It's available from open source labs. It's been around for a little while now, and it currently costs about £140, and that normally includes postage and getting it here, and it usually comes quite quickly. It covers 0 to 64 megs with 16-bit direct sampling with the same 2218 analog to digital converter. It includes a good quality programmable gain preamplifier and attenuator, and it can accept an external clock input if you want accurate clocking. It works with HD SDR, SDR console, and Uber SDR, which is currently my favourite application. Uber SDR provides a web interface, multiple decoders. It's really quite amazing. So this is the unit. This is an RX888. You can see it's remarkably simple. The bottom half here is the VHF section. So it has got a VHF tuner if you want to use that. But for most people, all we're interested in is the HF path to do HF through to 50 megs. And it's just that top line. So these are RF chips, preamp, etc., attenuator. That's the ADC, that's the USB chip. Very simple device, which is why it's quite cheap. So Uber SDR, it's a free application produced by Nathan MP9 PSY and his fellows. It runs on Linux, and it transforms the RX888 Mark II into a comprehensive all-band monitoring system. It's web accessible, can be shared with multiple users. It can simultaneously decode and report FT8, FT4, FT2, Whisper on all the bands at the same time, if your processor is powerful enough. Quite amazing. And it produces lots and lots of monitoring information on band conditions, signal to noise levels at your station, etc. So that's enough from me, really. I've put a QR code up there. And the QR code will take you straight to my Uber SDR. You can do it on your phone, you can do it on your computer, you can do it on anything. You don't need, it doesn't have to be Linux. It's only the server bit that runs on Linux. So if you take a photo of that or use your QR code to follow that one on screen, you'll find you're operating my receiver, and it can take up to 20 people simultaneously, tuning anywhere between 0 and 30 megs. So there we go. I've waffled on a lot, so I won't necessarily do a demo on Uber SDR unless anyone wants it. So we're now into questions, David, if everyone's still awake.
Lovely, Mike, thank you. Yeah, we're certainly still awake. I've always found this very difficult subject, being honest with everybody, and maybe you've done it as well. Most I'd say new radios coming on the market now by most manufacturers are SDRs of kinds, even though that part of it might be slightly hidden from us because the manufacturer's done all of the application, isn't it? But anyway, this is a great time to ask questions or make comments for Mike. To give you a chance to do that, though, I'd like Mike to reconsider what he last said, and it'd be lovely to see his demo, if you don't mind. Mike, if it's not too late for you, that is, of course. While Mike, we're going to let Mike do that now, and we'll come off his screen, I think, Tammy, just so that you can set it up. And if you do have anything though to say to Mike, and we'll bring it on to the screen. Oh, here we go. It's coming on now. So this is the demo of Uber SDR. Yeah, this is your favourite application.
It is. So this is if you follow that QR code, this is where you'll end up. This is the main interface where you can click and tune all over the place. This is currently on the 40 meter band, so you can see there's loads of USB signals here, LSB.
There is a lot there. What sort of, I can't, because it is very, very small for us, and we're looking at it in a studio monitor, so I think for people at home, it will be even smaller, Mike, although we can hear some contact there. What sort of bandwidth are we looking at there?
This, at the moment, you're looking at part of the 40 megs band, so from 7030 through to 7.2 megs.
So, sorry, I missed the part of that. What was it? 7 point?
From 7.02 to 7.2 megs.
So most of the band?
Yeah.
Oh, wow.
Oh, you can have everything. Look, if I do that, there we go. You've got 0 to 30 megs.
Oh, goodness me. So all bands. That's amazing, isn't it? And then he's using that RX888. Was it an RX888?
It is, yeah. And it's connected currently to a Wellbrook ALA 1530 active antenna. So just by rolling the mouse over the spectrum, I can just roll into anywhere I like.
Extraordinary.
I can tune around as quick as I like to anywhere. So if you want to get to the 20 meter band, here we go. So we can look at a bit of, oh, hang on. Let's go into here. So that's FT8.
Yeah.
So that's the FT8 segment on 20 meters.
So just to reiterate again, then the RX888 is about £140 from AliExpress, someone like that, direct from China. That isn't a lot of money for something that can do that along with the software, is it?
No. And if I just stop this a minute, and if I go into the admin configuration, I don't know how much of this you can see.
We see a fair bit, but I mean, we're looking at a first generation, as it were. I think everyone at home will be looking through a variable internet connections. I think Tammy may be able to electronically zoom into that, actually, with a bit of plastic, a bit of magic here. That might help people, but I could almost read most of that, Mike. Again, a reminder to everybody at home, though, please, we've got a couple of questions and comments for you, actually, more comments, but if anybody would like to say anything, because we're coming towards the end of our programme now, then please pop them on there. Here we go. Tammy has just enlarged that, I think. There we are. So that's a bit easier to see. So that's using the processor. Is it a very fast computer that you've got to do this?
Mine, it doesn't need to be. I've had it running on an Intel i5 11th gen or 10th gen. Perfectly happy on that. You can run it on a slower machine. This one actually that you've got here is running on an 11th gen i5 machine, which I got off eBay for about 200 quid. What I tend to go for, I've got several on here actually, is the NUCs, Intel NUC computers or similar. They're little boxes about 4 inches square.
Yeah.
they're often quite cheap, and they're usually quite adequate for doing this.
I don't suppose you need anything particularly high video cards or anything like that, do you? Really?
No, because there's no video to it really.
No.
It's all. I'm accessing all this through the internet.
No, I'm really glad you gave us a demo, because I think it's important. You know, at the end of the day, a lot of us are experimenters. That's at the heart of our hobby, after all. So, you know, how would you say? I mean, for someone like yourself who's very used to using Linux, this would frighten, I think, some people who are maybe used to a Windows or possibly a Mac environment. How difficult is it to think, well, I'm going to have a go at that and get one of these computers and do it? Is it not for the faint-hearted, or is it something that's nowadays relatively more accessible?
It's actually comparatively easy. You have to. The ubersdr.org site is very helpful.
Sorry, the say again?
ubersdr.org.
Right. Mm-hmm.
Their site is very helpful because there's step-by-step instructions as to how to install it. And they've got an install script on there. So you literally run that script and it does the whole installation for you.
Yeah.
The first thing you need to do, though, is install Ubuntu server.
Right. Okay. Yeah.
Now, in Practical Wireless, about 2 or 3 months ago, I did a full description of it, how to install it. I could probably resurrect that and put it on my website somewhere, or repeat that to someone. If someone's interested and want to do it, if they want to email me, I'll happily send them the instructions.
Either email Mike direct, or you can email me and I'll forward it on to Mike. I just think there's a lot of people who love experimenting. You know, when you mentioned at the beginning of your talk about these little tiny SDR dongles, the ones that are about a tenner, the USB dongles, and you know, they really were amazing little things, but it kind of, I think they've all run out of steam with it. And this little box, this RX888, really, when you think that the SDRs you were talking about, I'm not sure about the first one, the S-Buy, but I mean, certainly the Flexes are thousands and thousands of pounds, aren't they?
Oh yeah, they're big money.
Yeah. So this is a great way to, you know, much more affordable way to experiment.
It is. Oh yeah, I've got 2 of them here, and I'm using them for all sorts of experiments. And it's just so useful, because the other thing this UberSDR can do is I can decode FT8 on every band and report it to PSK Reporter automatically.
Well, I'm going to come to a few comments now that we've had, actually, Mike, because there's one very relevant to that. Steve G0KY says, a comment rather than a question. The RX888 is what we ran at the GB0 PSC personal space weather station in Baldock. It decoded all the whisper signals during the Eclipse experiments, which of course was just a week ago. And it feeds the data via cellular link to Whisper Rocks so that we can analyze the data as we want. So there we go. It's a real world demonstration of you know, how you can do this sort of stuff. Mario KD6ILO, welcome Mario. He says, I use SDRs that are R&D compliant with FPGA as I have experience, but yes, they are costly for most. And by the way, he also adds another comment on here. Great presentation, Mike.
Oh, good.
So very well received here. And Simon M0SIH says, a very interesting and informative evening on NARC Live. So it is, and it is really interesting to see this stuff. I'm not a software man. My head's in 80s and 90s logic gates and the early process, the 8080s and Z80s. That's what I'd learned when I was at college, and I did all my first stuff. And I don't think my head's moved on into the sort of software development area. And I know quite a few friends and colleagues, you know, it's the same for them. But this does just sort of feel, I'm not going to, don't worry, Tammy, I'm not going to quite yet spend £140 on AliExpress, I promise. But it does feel like something really exciting that you could just put in your shack and just look at all the bands like that. Amazing. Yeah,
you can dive around all over the place. And I've spent a lot of time over the last 2 months working with ChatGPT, writing software with ChatGPT to do all sorts of analysis for me. And I'm just gathering so much data from different sources and processing it. It's absolutely fascinating what you can do.
Just slightly aside then, because I know that AI has got a bit of a mixed rep at the moment, hasn't it? Let's be honest. But for experimenters like us, using it to compress and to analyze lots of data, how would you go about using AI then? ChatGPT is the one you've used for processing data. Is that straight off on your computer? Are you using that, or are you getting it from other sources?
So what I get it to do is I get it to write Python scripts to gather the data that I want. So I'm using my SDR, my RX888, to receive loads of bands, and I gather all the information from it. It goes into a database on my computer, and ChatGPT has written the software to put all that information off the RX88 or off Uber SDR into a database, and then I get it to write reports that I run on the database to give me the information I want, to extract the information I want.
Extraordinary.
So I've done all of that. I haven't written a single line of software. It has written them all. But I have to say, artificial intelligence is the wrong word.
Yeah.
There is no intelligence.
I agree with that, yeah.
There's absolutely no, it's stupid.
It's speed, isn't it? When I've been asked about this as well, Mike, with friends, family, and occasionally on broadcasting and things, I say exactly the same thing. It's not really intelligence. It's just the raw speed of the thing that is processing stuff now so much faster than it was years ago. Do you agree that that's really what it is? It's extremely fast and accessible because you can talk to it even.
Yeah, you can give it a quite complex task. I've given it quite masses of complex data where it's been able to work out trends and things very quickly. It is very stupid. It's also got Alzheimer's, and because it changes personality. If you have a long chat with ChatGPT about something that maybe goes on and off during a day, you will find a point where all of a sudden it sounds like you're talking to someone else, and it does that, and it does a reset. So it's just.
I haven't used it enough. I must admit, my own use of it really, apart from when it is used in browsers and things, almost without me realising.
Yeah.
I was up against it a few months ago for something for WRTC. Actually, I was writing an article and I had a photograph to go in the handbook, and it had a few hours before the press deadline. You'll know about this, I'm sure, because you write a lot, and and I really had this picture which I had to get rid of certain things out of this picture. And for the first time ever, really, I consciously used AI because I thought, well, I hear about this stuff, and I was blown away because what I found is you had to be very literal. You had to tell it everything. So it's no good just, in my case, I was trying to take something out of the picture. That isn't enough because you need to tell it what to put in its place. But in my case, this was a picture of a room which had some windows in it, and it had some vertical blinds. Actually horizontal blinds behind it, and basically I realised that I had to tell it to remove what I was trying to remove. It was actually a monitor picture, and but I said replace it with the blinds from the window, and sure enough, of course, it did it. I mean, I know that's minor stuff, but it can be a good tool to use.
It can. You just need to learn it.
You do need to learn it, and we don't want to get onto that here, but I just worry about it, obviously, for the impact it will undoubtedly have on some people's jobs and things like that. But for us experimenters, let's keep positive. This is a good tool.
Oh yeah, it's very useful.
And a lot of fun as well.
Yeah, I found it very useful to do things that I wouldn't even bother to try if I'd had to write the code myself or do it all myself.
Absolutely.
So it's been helpful. It does lie to you as well. I've caught it lying twice.
It's a mixed personality. It forgets stuff and lies to you. So there are a few warnings to using AI then, but so treat it with care, maybe.
Yeah, definitely.
Anyway, Mike, it's been wonderful to have you on the show again. This is really fascinating, and I'm so glad you gave that demonstration because I think that will show people exactly what you can do with a relatively low cost bit of hardware and a bit of experimenting. And as I said, that is at the heart of our hobby after all, experimenting. If it always worked, then there wouldn't be much fun in it, would there? So thank you for coming and sharing another subject with us, and we hope it won't be too long before we see you again.
Jolly good. Yeah, thank you.
Many thanks, and best wishes to Elaine as well.
Will do.
Thank you. Cheers. Bye. Bye.
Bye.
There we are. What a wonderful evening of I mean it wasn't. I mean, it wasn't heavy exactly, was it? But there was a lot to take in. But then to see it at the end and see what you can do with it was truly wonderful. So thanks very much to Mike G4WNC for that talk. Now we're just going to tell you what's happening in the coming week. However, there is something that we've added just at the last moment before the show came on air. Now, SSB Field Day is on the 1st of September this year. It's always the first weekend, I think, in September, and that must be it. And over the years, sometimes, but not every year, we've run it from here. But regardless of where it's run, what we want to know from you as NARC members is, would you like us to put on an SSB Field Day station on the 1st of September? We really do need the support. We don't want this being set up by members of the committee and it's maybe you're not very interested. So we're just going to ask you now to be proactive. Let us know. Drop me an email, the usual address, radio@dcpmicro.com. Here we are. It's on the screen now. It's the same address it's been for years. radio@dcpmicro.com. If you would be interested to coming and working and helping set up and operating on SSB Field Day Station on the 1st of September. And if we get several people interested, then I'm sure we're going to put it on. So please respond to that. I'll also pop that on the newsletter as a reminder as well.
I don't think it's the 1st of September because that's
Isn't
a
it?
Tuesday. Is it the first weekend of September?
Oh, okay, possibly. Well, this is something, I'll be honest, Andy M0NKR messaged me early on to say that. Oh, you're right. I'm very sorry. It is the first weekend in September. I beg your pardon.
So that'll be the 5th and the 6th.
5th and the 6th, yeah. I thought it was a bit strange, but maybe just a coincidence. No, 5th. So the 5th and 6th, the first weekend of September. If you're available and you would like to operate, help us set up, run, whatever, if you're interested, please do let me know. We'll kind of make a little roster up, and if we've got several of us, then I'm sure Andy and his colleagues will set up that. But that is it for this week. Actually, we're going to be away now for 2 weeks from NARC Live. We're going to be meeting at the school for the next 2 weeks concurrently. So don't forget, this Sunday, it's the Sunday Fun Fox Hunt by the Foxes, leaving at 10 a.m. from Rackheath Village Hall. But please do let me know if you're going to take part this time. And we'll get you booked in for some food as well. Also, in the evening of Sunday, as usual, the GB Tourist News at 7 p.m. on GB3MB, and also on that same repeater at 7:30 on Monday night. It's the Monday Night Net. Do join in with that. It's a great way to have a marvel and a chat with other like-minded friends and colleagues. And then next Wednesday, as I said, and the Wednesday afterwards, we'll be at the CNS School for Social Informal between 7 and 9:30. And of course, we're happy to send this card to anybody you let us know. I think that's covered everything. Also, mystery objects, we're getting very low now on them. We're just keeping ticking along. But if you've got a mystery object, then please do let us have that. We'll see you again here in 3 weeks' time, I guess. Yeah.
Yep.
But until then, from Tammy M0TC.
Bye-bye.
And from me, David G7ERP. Take care of yourselves and look after each other. Bye-bye.